Today, we will announce the overall superstructure by securing what was lacking in the previous announcement. Present the first review, the second tapering and setback, and finally the pinnacle in the table of contents. First of all, we believe that there are some deficiencies in the last presentation, so we will review the structure of the superstructure in this presentation as a result of this presentation. A depth of 10 to 20 meters is a weak alluvial layer of clay or sand. This location consists of the base of various thickness of sedimentary layer formations such as silt and sandstone. In addition, the interface is always overlapped by an irregular slump zone in which the canyhill material is soft and eroded jointly with limestone, so it is not suitable as a foundation. Therefore, the friction piles were set different heights depending on the shape of the canyhill, avoiding the slump zone. These 5 drifts have cores attached to support the entire building. If you look at the cross-section of the core, there's a core in the middle for shear reinforcement. It consists of a ring beam and 16 per-meter columns. The core and ring beam per-meter column are connected through a steel frame, so the force is divided by half. The central structure of Petronas Twin Tower is based on scale core, 23 by 23 meters basically concrete attached to a per-pier ring of 16 concrete columns. This inner core system has strength to resist 50% overturning moment which caused by lateral force. The towers rest on a concrete slab shared, which in turn is placed on a forest underground concrete and steel piles. The concrete ring beam on the steel frame is a form in which the concrete slab is attached as a simple shear joint. It is transmitted under the load via the ring beam. This is a diagram of the overall bending moment of the building. If there were no structural reinforcement, it is expected that the building would have been bent like this due to lateral force. As I explained earlier, there are cores or columns which are connected by a steel frame. For structural reinforcement, the outrigger is installed on a 38th to 39th floor of the building and is additionally combined with a core to reinforce the shear force. Next, tapering and setback. Looking at the shape of many skyscrapers, including the Petronas Twin Towers, you can see that every one is getting thinner as they go up. These structures are called tapering and setback. In the case of skyscrapers, the wind load increases rapidly as you go up to the upper part of the building. So many kinds of this high-rise building, including Petronas Twin Tower, using tapering and setback for the stability of the building under high wind load. You can see the lower part is shape of cube, and by ascending, the building gets narrower. This continuous shape of left figure is setback and continuous shape of right figure is tapering. They used both setback and tapering in case of Petronas Twin Tower. In the development in high, 2 towers were designed to be topped by concealed pinnacle at the top of building. Walls of the upper floors are also inclined inward to taper and converge at the pinnacle. They are designed with slight setback at 60th, 73rd, and 82nd floor over 3-story height with sloping column. To look deeper in the advantage of the sloping column, we discussed it by comparing with the straight column. And there is particular force from above and lateral wind force. There must be reaction force from the lower part and also the lateral reaction force to the wind load. In the case of a straight column, slab get all the lateral force, while in the case of a sloping column, the whole structure resists all the lateral force. They can have advantage in lowering the load to the slab. By using a sloping column, we can get advantage for 34% increasing of lateral stiffness in height of 450 meters with high lateral wind load. Also, if we use the box-shaped building, not a trapped shape, the area against wind get bigger, and this makes building vulnerable to strong wind load for high-rise building. This tapered shape helps building to resist less area by declining area against wind. Here is interesting chart about tapering angle. When taper angle get bigger, building get more lateral resistance. Because our building is 80-story building, and also its tapering angle is 1.5 angle by our own calculation. This building get more about 25% lateral resistance compared not using the tapering shape. In addition, these tapering and setback structures have a vortex shading structure in which the building is not directly hit by the wind due to the decrease in area as fast wind is applied to the skyscraper. To summary, the upper part of Petronas Twin Tower kept the setback and tapered shape by using the sloping column. Due to this sloping column, it got more lateral stiffness. The advantage of decreasing the area against wind and the lower lateral displacement. Last, the vortex shading effect. All of this helps this high-rise building to resist very strong wind at higher elevation.
Accordingly, the Malaysian government raised the height of changing the pinnacle, which was originally designed to be 50 meter height, to about 73 meter in 2 times to create the world's tallest building. As the height of pinnacle increased, the self-loaded and wind load were considered and recognized as a building. The height of the roof of the Petronas Twin Tower is 319.2 meters, but the pinnacle was included in the height calculation, giving it the title of the tallest building at 451.9 meters. Kuala Lumpur's specialty is metal tin. They wanted to give similar building at Petronas Twin Towers. Due to this, they considered of using material that has metal texture and feel heavy. For maintaining this building, the Petronas pinnacle was made entirely of stainless steel. The shape of the pinnacle formed a trapezoidal shape. The center part had 15 links or with various diameters. Separate by ringboard zone, the upper pinnacle and the lower pinnacle. In the case of upper pinnacle, it consists of circular cross-section rather in a smaller form, and the lower pinnacle consists of an outer sheath from the roof and an inner ladder. These pinnacles are secured with mass anchor approximately 14 megaton from the roof, with damper and spiral board at the top to counter lateral forces. In addition, a pinnacle contains aircraft warning light and equipment from building for external maintenance, each consisting of 26 segments. Since the Pinnacle was to have a final weight of 170 tons after installation, it depolarized 8 jacks and 4 lifts with withstand 25 tons, creating a jack-up system capable of lifting up to 200 tons. In addition, the guide rail method was used to reduce the impact of wind load during lifting operation and to reduce the need to correct Pinnacle after completion of the work. The guide rail method is to attach a roller to the part that touches the Pinnacle frame, and the roller moves along the frame to distribute the load. An advantage of this jack-up system and guide rail method are mechanical locking, so it can be safely secured and the rise and fall speed can be adjusted using the eccentrically. The structure was raised to the position of the Pinnacle using a jack-up method. The following structure was constructed on the ground, while connecting the existing and new structure with welding. In this way, the entire stainless steel part of the Pinnacle was fixed to the mast anchor, and the jack-up system and guide rail were dismantled. Then the Pinnacle was fixed to the outer frame once more, and the frame was loaded with the outer material.